Hi guys, welcome back. We're going to be looking at the fundamental theorem of calculus. And so kind of as we're taking a look at this, trying to do something a little bit different here. I'm going to try to remember that I have two monitors going. So we'll see how this works. But the fundamental theorem of calculus is something that is really important. And so kind of the whole um, second half of calculus is based on this fundamental theorem of calculus. So we're going to jump into and kind of see how this works and how this is connected to what we've done before, which is this idea of net area and accumulation. All right, so we've just taken over as the manager of a struggling umbrella company. We have a rate function that we're working with. And so our rate is going to be given by this function g of t. And we're only looking at between 0 and 14. And our factory only opens at 6 a.m. And so it gives us our g of t below. T equal to 0 would be 6. And I think 4 p.m., no, 10 would be 4 p.m. and so on. So kind of this idea of adding up what our time is as we take a look at it. Now, when we look at this problem, the first question that we're going to be looking at is going to be this idea that after we have a leisurely breakfast, we're going to arrive at work at 9 a.m. And we want to write an expression that gives the number of umbrellas that have been produced before we arrive. Now, remember that the uh, company opened at 6 a.m., so that was t equal to 0 and 9 a.m. would be t equal to 3. So we're looking for the accumulation. I'm going to remind you of that term. And the accumulation of umbrellas from 0 to 3 hours. And that would account for our 6 a.m. to 9 a.m. that we're looking at. And if you'll remember that area under the curve, if we're looking at it from 0 to 3, which is right there, that when we look at that, that's going to give us the net accumulation of umbrellas that have been produced. And that area under the curve is going to be the integral from 0 to 3 of the rate function. And the rate function is what's going to go inside. So that's going to be the g of t dt that we have working here. So that's the idea that kind of starts to tie our definite integrals that we were working on in the last few note videos to the accumulation that we're doing today. Now, in this, it's going to ask us like roughly how many umbrellas were produced during that time. So you can remember that basically we're just trying to estimate what our actual area is under the curve. And I'm going to use, I think out of the methods, left sum, right sum, midpoint sum, trap sum, I'm going to use the trap sum. So, and I'm just going to do one quote unquote trapezoid. It's actually going to end up being a triangle because we're going to take from 0 here and do g of 0, and then we're going to calculate the height here. So this would be g of 3. So 3g of 3, and the one down here would be 0g of 0. And we'll use those and calculate the area under the curve. Now, of course, it's going to be a little bit of an underestimate, but that's okay in terms of that. So I'm only going to use like T1, a trapezoid sum with T1. So remember, we take our two quote unquote bases, and yeah, I do know one of them is 0, but that's fine. So we're going to do g of 3 plus g of 0. We're going to divide by 2 and then multiply by the height, which you remember is the width down here at the bottom, which is 3. And notice that that actually is exactly the same as the area of the triangle because g of 0 is going to be 3. And so when we look at that, adding it up, it ends up being 1/2 g of 3 using our formula that we have is the 20t minus t squared. And 20t minus t squared is going to give us 51 for this value right here. And so it's going to be 1/2 of 51 times 3. And you'll see that that's exactly the same as the area of that triangle, which is a fairly good approximation for this. So this would be 76.5 umbrellas. And again, to kind of remind you about what the units would be for that, that when we're looking at this rate, the rate 51 over 2 that we had is going to be umbrellas per hour. times 3 hours. And that's why we're going to end up with units of umbrella for that. All right, now we're going to take a look at the next problem, which says that we want to go to lunch break at 12:30, and we want to write an expression that gives the number of umbrellas that have been produced that day up until your lunch break. So again, this is going to be the accumulation from 0 up until 12:30, which would be 6.5. And so when we take a look at that, we're just simply going to do the definite integral from 0 to 6.5 of g of t dt. And again, the idea is that if we want to estimate that, if we come back down here to our curve, we basically just want to kind of do the whole idea of the trapezoids again. We're going to be going to 6.5, which is approximately there. And I'm just going to do I'm going to do a trap sum with 2 trapezoids and add that area in right here under the curve so that we have the 2 trapezoids. All right, so now coming back down here to the actual formula, T2 would be our estimate of this definite integral. We already have our 76.5 from the previous, so I won't calculate that again. And then we're going to have g of 3 plus g of 6.5, the two bases, divided by 2 times the width, which is going to be 3.5. And if we add all that up, and I'll leave the arithmetic to you to calculate each of those, you're going to end up with 319 umbrellas as an estimate for that. All right. Now, the next part is kind of the important part. So I'm going to put a star here by 3 because this is where we're going to really get into the heart of what the fundamental theorem of calculus says. I had a little bit of technical difficulty there, so we're coming back in and we're going to look at this equation involving an integral for a function of f of x. And like I said, this is going to be super important for what we're going to look at for the fundamental theorem of calculus. So what I want to do is, like I said, the idea here is that the integrals that we were looking at before, I'm not sure when we got cut off there, so I'm just going to go back, that the integrals that we were looking at before, here at the accumulation from 0 to 6.5, and then the accumulation from 0 to 3, that both of those, when you take a look at them, have the same beginning bound, the same lower bound, but yet they have different input values for what the upper bound is going to be. So what we're going to end up doing is that input is going to be the upper bound. So we're going to start at 0, but we're going to go up to x. So our input is the ending value of where we want to stop the accumulation at. Our integral had our function g of t dt in here. Now I do want to talk a little bit about the notation for this because this is something that's kind of important as we go through the fundamental theorem. This function, this is called an accumulation function. Accumulation from, in this case, 0 to x is going to be this f of x. Your variable here and here should match because the input that we're changing is going to be that upper bound. The variable that is located over here in the actual inside of the integral right here, that is what we call a placeholder variable. And it's just holding the place for the actual input to the function, which is going to be the upper bound. So I'm just going to say, remind you that that's a placeholder variable. You cannot name, like the variable that's here and the variable that's there cannot be the same variable. They have to be different variables because one represents your input to the accumulation function, the upper bound, whereas the other one is kind of just a placeholder for the rate function that you're looking at. And we'll see a little bit more about, as we work through this, how this is going to be working. So for example, if I wanted to calculate f of 3, which is what we've done above here, our accumulation from 0 to 3 was 76.5 umbrellas. So our f of 3, and remember that was an approximation, would be 76.5. If I was calculating f of 6.5, our net accumulation of umbrellas from 0 to 6.5 hours after we opened, that one ended up being 319 umbrellas. And so the idea here is that this function represents the net change in umbrellas that were produced from time 0 when the factory opened till our ending time that we are setting by the input variable. Right? Now, an important thing about this accumulation function, and kind of this is the first step of the fundamental theorem of calculus, so this is like FTC part 1, that what if I wanted to find f prime of 8? So it's the idea of recognizing what that represents. So f prime of 8, that's going to be the rate of change in the number of umbrellas accumulated from when the factory opened at t equal to 0 up until 8 hours after they opened. And so the key idea here is for you to recognize that this is exactly the rate function that they have given you, except this rate function is really now going to be g of 8 because that is the rate. The rate function is inside of the integral here. So when I ask for the derivative of f of x, then the rate function is the function that's on the inside. So kind of recognizing how these are related to each other. And hopefully you'll start to remember, like kind of as we did anti-derivatives and stuff, that the function inside the integral is the derivative of the function that's on the outside. And so that's something that you're going to be thinking about as we do this. So our f prime of 8 is really the derivative with respect to x of the integral from 0 to x of g of t dt, put parentheses around that, and we are evaluating that at x equal to 8. And so that's why we're getting our g of 8. And so, and if we were to plug that in just into the function, because we already have it, that would give us 96. So if we had 8 times 20 minus 8 squared, that would equal our 96. Now, in terms of the units of this, remember that this is a rate. So this rate is going to be in umbrellas per hour. Umbrellas per hour, because the rate function in here is umbrellas per hour. So we're taking the derivative with respect to x, the number of hours that we have been accumulating these umbrellas that are there. All right, now the second question that they had here is this idea that when is f of x changing the fastest? All right, so f of x is changing the fastest. Realize that this is really an optimization problem. So f of x changes the fastest. We're looking for the max speed that we're looking at. Now, we're luckily for this one, our rate function, which is our velocity, okay, remember this is the absolute value of the derivative, which in this case is g of x. So we want the max speed, and g of x, since it's already positive for the entire 0 to 14, which is what we're doing, we can actually just use g of x for that. And so our idea here, okay, is that we want to find the max speed. Now the max speed, let's talk about how we would do that. This is on a closed interval, so I do need to do an EVT argument. G of x is continuous on my 0 to 14 because it was a polynomial, so we're okay, EVT applies. The next thing that we're going to do is we're going to calculate our derivative, g prime of x, and our derivative for this one is going to be 20 minus 2t, and that's going to equal 0 at t equal to 10. So for our discussion, we need to look at our input of 0, input of 10, and 14, and calculate the rates of those to determine the max or the min. Went ahead and finished this out for you. Come back to part 2 of this video.